Welcome again. This is Mr. Brian, and we're going to be talking today, part three. This is a part three discussion on quantifying matter, the final topic, part three. And what we're going to be doing today is we're going to be talking about reviewing section 11.1, and then we're going to jump back to section 2.2 to talk about some ways of problem solving, and then we'll finish up with a review for 11.2, which essentially is conversion of mole problems to more challenging ones that we've been doing. So let's get started. What you see here is kind of the mole map, right? And it's a recap of 11.1. So we've learned that the mole is this quantity, right? Very similar to like what we know about a dozen, right? So we know that a dozen is equal to 12 stuff, whatever that stuff is, right? So in this case here, a mole is equal to this many particles, right? Now, the particles here could be identified as anything, molecules, in this case, atoms, right? And very similar to what a dozen means, like you can have 1 dozen is 12 roses, you can have 1 dozen is 12 balloons, right? And so on, right? Now, what's different about a dozen and what's different about a mole is essentially the mass of that amount, right? The mass is always going to be different because it depends on what the particles are, right? So like here in this case, like 12 roses will have a different mass than 12 bowling balls, right? Or 12 balloons, right? In this case, a mass, a molar mass, which we deemed it, is going to be found on the periodic table. So for instance, if this is like carbon or this is like iron atoms, right? You're still going to get this many atoms in a mole, right? But in that mass, the mass of each of those little, bags, those moles, those counting stuff, you're going to have a different mass, which is found on the periodic table as, in this case, carbon is 12.011, which is found on the periodic table. And then here for iron, it's going to be like Fe, like I think it's like 55.9 or something like that, right? It's the bottom number. So the mass is different, right? So whatever amount in 1 mole that you see on the periodic table, which is 1 mole, you'll have this many things, and that many things, if it's atoms, it's going to be this much mass, right, on a scale, assuming that you use no tray or anything like that, okay? So let's continue on with this idea. So now I'm going to be jumping back to section 2.2 to talk about some ways of solving problems using called the dimensional analysis method. Sounds like a fancy term, but don't fret. I'll help you out here. So dimensional analysis is a way of solving problems that focuses on units. So we're going to be focusing on 2 units, right? Because we want to get rid of a certain units that were given, and we want to have a new units towards the end, right? This is what a typical dimensional analysis setup looks like. You have a given value here, which is in some sort of units, and you multiply it by a ratio, which I'll talk about in a second. And this ratio contains 2 units, right? And you're going to get your answer in a new form of units, your desired units. So what is this ratio that we talked about? What is this thing here? So this is called a conversion factor. So conversion factor are essentially a ratio. There are units that are 2 different numbers, but the units together, the values of these equal the same thing. So consider this example here. So you already know that 1 minute is equal to 60 seconds, right? If I say 120 seconds, automatically your brain knows, yeah, it's about 2 minutes, right? Same idea, like if I say 1 foot, you may be thinking it's also the same thing as saying 12 inches. Now notice how the numbers are the same, right? I'm sorry, the numbers are different, excuse me, the numbers are different. But what's the same is the value that both contain. Like, for instance, if I talked about in class, if I ran 4 laps around the track, you may say I ran 1 mile. Now, again, the numbers are different, but the values are the same because 1 mile is 4 laps, right? So you see how the units are different here? The units are different here. That's essentially what dimensional analysis attempts to do. We try to focus on the units, and we try to focus using a conversion factor to help us convert from one given unit to another given unit. And notice that the units that we want to convert into are always on top. And the units that we have, essentially, we want to cancel out so mathematically they can give us the new units. For instance, like in math, if I had x times y and I am multiplying, I don't know, y, no, x over z, right? Or x over y. That's what I want to do. X over y, excuse me, right? I'm going to get x squared because the y's cancel out, right? So it's very similar to that. And the numbers, the conversion factors, they're essentially ratios, right? And as you can see, we can flip these conversion factors into a certain ratio depending how we want to use them. All right, enough talk. Let me show you how this looks on a real problem. Okay, let me erase this stuff here and show you. Okay. So take a look at this example here. If I give you 5.0 times 10 to the 10 seconds, calculate the amounts of minutes that this given value is. And then when you're done with that, try to calculate the amount of hours. Let's do this together. So the first thing that I want to do is I see that this is called the given, right? So this is the given right here. And what do I want to do? I want to write down the given. Okay? So there's my given. And notice that I kind of wrote it in like a kind of almost a table. Similar here. We're multiplying across and dividing by the bottom, right? The question is, what is my conversion factors going to be? Well, we already talked about the conversion factor in this example as, minutes and seconds. So you should know you should know your conversion factors. So I got 60 seconds is 1 minute, 60 minutes is 1 hour. The question is, if I want to convert to minutes, which one of these will I use? Well, you probably know that you're going to use this one here. But how? Is it going to be 60 over 1 or is it going to be 1 over 60? Well, remember that we want to try to cancel out our given units, right? So we're going to go ahead and use 1 over 60. And if you notice here that the seconds cancels out, and so all we're doing now is we're multiplying 5 times 1, and then we're dividing it by 60. And remember scientific notation method, we leave this out and carry it over because there's no other exponent that we're multiplying. So these three numbers here gives us 0.0833, and then we move this and we reformat it scientific notation. We move 2 spots to the right. We got to take away, right, 2 exponents. So we'll get 8.33 times 10 to the 8 minutes. Okay? Now, let's try how that works with hours. Now, again, this number, although is different from this number, right, they have the same value. Okay? So we're just converting. So I'm going to go ahead and write this hour problem right here for you. So I got 8.33 times 10 to the 8 minutes. And so what I want to do is I want to find my conversion factor. And my conversion factor, let me erase this real quickly. So I have some spots to use. Erase that. And then I'm going to convert. And I need to know the minutes are going to be at the bottom and the hours are going to be on the top. Because the minutes have to cancel out. The question is, what numbers do I put here? Well, I know that that's my conversion factor. So let me write the 60 by the minutes and the 1 by the hour. And so now what I'm doing is I'm going to multiply across and divide by the bottom. So if I get my calculator, I'm going to get 8.33 times 1 divided by 60, which will get me 0.139 rounding, and then times 10 to the, 8, because I haven't touched it yet, right? So hours. Now I move the decimal over to the right. It becomes 1.39 times 10 to the 7 hours. And there is my answer for hours. Again, this number is different from that number, right? But essentially it's the same value. All right, moving on. So now this is 11.2, and in 11.2 we're given more challenging problems, just simply converting from moles to atoms to mass, right? So what you need to do here is we're just going to need more practice, and I'm going to give you an example of how to do this one. So here we're given that 2.4 grams of iron, right, is on this scale, and I want to know how many atoms are present in here. So how many atoms are present in that spot if this has a mass of 2.4 grams? So the first thing I do is I write my given. So 2.4 grams of iron. Second thing that I need to do is I got to identify my conversion factors. Now here's some examples of conversion factors, two of three possible conversion factors, which you have, 1 mole is equal to this many items, right? And we can flip this as 1 mole over 6.02 times 10 to the 23rd, or 6.02 times 10 to the 23rd over 1, right? So these can be used interchangeably, the ratios. It depends on how we're using them in this problem. So back to here. So we need to notice that this gram's got to be somehow canceled out. And we want to get atoms, right? So here are 3 conversions that I know. I know that 1 mole is equal to 6.02 times 10 to the 23rd atoms. You got to know that. It's got to be memorized. Then I know that 1 mole is equal to 55.9 grams. This is called the molar mass. We find that on the periodic table, the periodic square. Now, then I have 55.9 grams is also equal to that many atoms, 6.2 times 10 to the 23rd atoms. Now, which one of these conversion factors could I use? Well, I can use any of them, right? Essentially, I can use grams to moles, and then I can use moles to atoms. But I'm going to try to use both of them at the same time. I'll use grams to atoms because I want to really find atoms. So when I plug it in, right, here's my 55.9 grams. It goes at the bottom because my grams are canceled out. And then I have my 6.02 times 10 to the 23rd on top, right? And again, these two, let me review, let me erase this. These two are essentially equal to each other, right? They have the same value, right? That's why it's a conversion factor. And as we multiply it across, we'll get 2.4 times 6.02 divided by 55.9. We'll get 0.258 times 10 to the 23rd atoms. Now, if we change the scientific notation, move it 1 decimal to the right, we'll get 2.58 times 10 to the 22nd atoms. And that should look right to you, right? I mean, the idea is, man, I got 2.4 grams, right? I have less than 1 mole because 1 mole is 55.9 grams. So if I have less than 1 mole, my answer should be less than this many atoms. So get in the habit of trying to predict, right? Trying to predict your answer before you solve it to make sure that you're on the right track. That clearly is way less than this amount of atoms, which just sounds right to me. So you try this next problem out and see if you have any questions or concerns or have a hard time with it. Hit me up at tutorial and I can help you out. Good luck.